Good morning. Day two, we're going to look at logarithms. Yesterday, we were looking at exponential functions. A logarithm is basically just the inverse of an exponential function. So we first need to know how to convert from exponential functions to logarithmic functions. Remember back in Unit 1, we converted algebraic functions to inverses, and we switched the x and the y's. Well, you do the same thing for exponential to logarithmic. A log function is in the form of log to some base and some value equal to y. Remember, exponential function, we're going to write it as x equals b to some exponent y. So we're going to keep the same base and put it beside the log. So this b, the big number in the exponential function, comes down to be the little base in the log. And then we just switch the x and the y. Okay? We keep everything the same except switch the x and the y. So let's do some examples. The base in this exponential function is 5. The exponent is 3, or the y. Here's our x and our y. Here's our base. If we switch them, we're going to do log base 5, and we're going to switch the other two numbers. The 125 comes here, and the 3 comes here. So we keep the same base, and we switch the other two numbers. Okay? If you want, you can switch it and write it the other way. Either one's fine. I prefer to start with the log. Okay, next one, the base is 2, and we're going to switch the 64 and the 6. So it should be log base 2, 64, and 6. Or you can write it this way. So for those that are questioning this, this is really how we should write it. The base stays the same, and we switch the other two. This will help out a lot when you get to solving equations with exponential and logarithmic functions. Next one, we have a base of 1/2, and we're going to switch the 5 and the 1/32. So log base 1/2, the 1/32 comes over to next to the base, and the 5 goes on the other side of the equation. If we want to take a log to an exponential form, we do the same thing. We're going to switch the x and the y. The log goes away. So we have a base of 2, and we're going to switch the 16 and the 4. So it'll be 2 to the 4 equals 16. So there's my base, and we switch the 4 and the 64. Excuse me, the 4 and 16. Here we have a log base 3, so it's going to be 3 to the 2 power equals 9. You should know if you're right because 3 squared does equal 9. Last example, we've got a base of 81. We're going to raise it to the 1/4 power, and it's going to equal 3. You can also check these in your calculator. If you type in 81 with an exponent of 1/4 and hit enter, it'll be 3. Evaluating logarithms. You can do this in the calculator. We can also do it algebraically. We're going to make log base 2 of 8, set it equal to x. The first thing you need to realize is that it's easier to evaluate when it's in exponential form. So let's convert this to exponential form. I'll have a base of 2 and I'll switch the x and the 8. So now I have an equation I need to solve for the x. In order to do that, I need to have them in the same base. Bases are usually the prime numbers. 2, 3, 5, 7. Those are usually the bases. So 8 in a base of 2 is 2 to the third power, because 2 times 2 times 2 is 8. Once you have them in the same base, the bases cancel each other out and you have your answer left. All right, let's look at another one. We're going to make it equal x. I'm going to write it in exponential form. So it'll be 3 to the x equals 81. 3 is a prime number, so I want to make 81 a base of 3. What exponent can I raise 3 to equal 81? Well, 3 to the fourth power equals 81. Now that I have the same base, those go away, and I'm left with x equals 4. Next example, make it equal x, raise it to, or convert it to exponential form, so it'll be 2 to the x equals 2. They're the same base. However, what is my exponent on this 2? It should be a 1, we just never write it. So if I cancel the 2's, I've got x equals 1. Next one, set it equal to x. I'll have exponent form of 8 to the x power equals 1. Any number raised to the 0 power equals 1. So when you have it equal to 1, you know x is going to be 0. What do you notice different about this one? Well, this one, they don't list a base. Anytime you see a log with no base, it's understood to be base 10. That's our natural counting system base. It's based on tens. So if I write it in exponential form, I'm going to get 10 to the x equals 1 over 100. 1 over 100 is not in a base of 10. So I need to write it as a base of 10. 100 is 10 to the second power. So 1 over 10 squared is the same as 1 over 100. Well, how do you write 1 over 10 squared without it being a fraction? If you remember all the way back to your exponent rules in Math 1, the exponent changes to a negative. So it's 10 to the negative 2. Now I have them in the same base. X equals negative 2. Next one. Convert it to exponential form. 64 to the x equals 16. Neither the 64 or the 16 are a prime number. I need to make them into a prime number. 64 and 16 are even numbers, so I should be able to get it down to a base of 2. 2 to the what power equals 64? Well, 2 to the 6th does. And we keep the x there also. 16 is 2 to the 4th power. I now have them both in a base of 2, so the 2's cancel. And now I have a little algebraic equation I need to solve. I need to divide both sides by 6 and simplify. And I got x equals 2/3. We'll look at properties of logarithms. These are things that never change. Okay, they're rules that always apply. The log of any base of 1 is always 0. So if this number is 1, at any time your answer is 0. If you take the log of a base and the number that you're taking the log of is the same, so here log base A of A or log base 5 of 5, it always equals 1. Here we have a log base A of A raised to an exponent. Well, the log base A of A sort of cancels each other out, and you have equal to whatever the exponent is. So as an example, log base 7 of 7 to the 2 power would equal 2. Next is an exponential form with a log in the exponent. If you have a exponential base of A and the base in the log is the same, these sort of cancel each other out and you're left with x equals x. An example of that would be, let's go 3 log base 3 of 9. That's going to equal 9. And number 5 here, if you have log base A of some number equals log base A of another number, those log base A sort of cancel each other out, just like we had in the prior examples on the other page, and you would have x equals y. So an example of that, log base 2 of 10 equal to log base 2 of x. You would have 10 equals x. We'll run through some examples. Here we have log base 5 of x equal to log base 5 of 8. Remember, these two things sort of cancel each other out, and x would equal 8. Remember, anything that a log with a base of 1, when that number is 1, x always equals 0. Number 3, log base 5 of 5 to the third. You can look at it as the log base 5 of 5 cancels each other out, and x would equal 3. Okay. Here's another symbol. You can find this on your calculator. The log is right beside the 7 on the calculator. This is ln. It is right below log for log. Ln is the natural log. Natural log is the same as log base e. So natural log is the same as log base e. So if I have the natural log of e raised to the 5th power equals x, what is my answer? Well, my answer, if I convert it, natural log of e is the same as log base e. So these sort of cancel each other out now. And I have 5 left as my x value. Here I replace, I've got e. This is an exponential form. E raised to the natural log of 3. The e and the natural log sort of cancel each other out. And I have 3 left. This is the same as you would write e to the log base e of 3 equals x. Those cancel and you got 3 left. Last example here. I convert the 1 over e squared to e to the negative 2. The natural log and the e sort of cancel each other out, and I have negative 2 left. So now let's look at some graphs. Look at some graphs of logs and exponents. Remember, a logarithm is just the inverse of an exponent. So the graph of the logarithmic function is going to be the graph of the exponential function reflected over the line y equals x. Remember back from unit 1, if the inverse of a function, if you graphed them both on the same graph, they would reflect over the line y equals x. This dashed line is the graph of the line y equals x. So if we graph 2 to the x power, put some x values in there, 2 to the 0 power is 1, 2, 4. We graph that 0, 1, 1, 2, and 2, 4. Let's go one more. 2 to the 3rd power would be 8. So we would be out here at 3 and 8. So if we graph that, it looks something like that. That's 2 to the x power. if we want the inverse, we don't really need to do an XY table for log base 2 of x. We can just flip these points over the line y equals x. In other words, the x and the y switch. So it'd be 1, 0, 2, 1, 4, 2, and 8, 3. Right. So this is log base 2 of x. So if you fold this graph along that dotted black line, those blue and red graphs would meet. Remember exponential properties? It's in this format, y equals a base raised to an exponent. The domain is all real numbers. You can write all real numbers with that symbol. Range is 0 to infinity. The y-intercept is 0, 1, and the horizontal asymptote is y equals 0. So when we have the inverse of exponential, the log properties are sort of the opposite. Here's the format for the log function. The domain is going to be what was the range of the exponents, 0 to infinity. The range for a logarithmic function is going to be what it was for the domain of an exponential function, so all real numbers. We're now going to have an x-intercept, not a y-intercept, of 1, 0. And we're going to have a vertical asymptote at x equals 0 versus having a horizontal asymptote at y equals 0. And if a is greater than 0, this function is increasing. So there's all of your properties for a log function graph. So we want to graph and find the domain and the vertical asymptote for log base 3 of x. There's different ways you can go about graphing this. Of course, number one, you can put it in your calculator. Go to table and get some x and y coordinates. Number two, you can convert the log to exponent form. In this case, it would be 3 to the x equals y. And plot it and do the inverse. So graph and reflect it over y equals x. So if you don't have a calculator, number two is the best option. So if we graph y equals 3 to the x, 3 to the 0 power is 1, 3 to the 1 power is 3, 3 to the 2 power is 9. If we plot those points, and and we graph it over the line, y equals x, I can flip my points. And I can plot those and I'll have the graph of log base 3 of x. So 0, 1, we'll have 3, 1, and I'll have 9, 2. This is my graph of log base 3 of the x. So I have a vertical asymptote at x equals 0. It never crosses the y-axis. My domain is 0 to infinity. Domain is the x values. I go from 0, but I don't include it, all the way out going toward infinity. Next one. Log base 3 of x plus 2 inside parentheses minus 1. Well, that's the same thing as our graph previously, except I'm going to move it left 2 and down 1. So if I graph my log base 3 from the previous graph, I had points at 1, 0, 3, 1, and 9, 2. So this was my graph of log base 3 of x. And I want to shift that graph left 2 and down 1. So every point is going to go left 2 and down 1. Left 2, 1, 2, and down 1. Left 2, 1, 2, and down 1. Okay. So if I draw it on this one, it looks something like this. So this is my vertical asymptote at -2. Vertical asymptote at -2, and my domain goes from -2, but I don't include it, all the way out to infinity. Okay. Next example, y equals negative log base 3 of x plus 1. Left and right, then reflect it, then up and down. So if we reflect the asymptote on the y-axis, reflections. So if I graph this, this is our same graph of log base 3, but I'm going to reflect it in the x-axis, and I'm going to move it left 1. So if I graph my log base 3, three to the 0 power is 1, 3 to the 1 power is 3, 3 to the 2 power is 9. And I reflect that, I'm going to get points at 1, 0, 3, 1, and 9, 2. So this is log base 3 of x. And now what I want to do with this is I want to reflect it in the x-axis and move everything left 1. So if I reflect it in the x-axis, that point's going to stay right there. This point at 3, 1 is going to come down here. This point at 9, 2 is going to come down here. And it's going to look like this. That's negative log base 3 of x. And now I want to shift that red graph all the way over to the left 1. Shift everything to the left 1. So these points right here, if I shift it left 1, I'm here. If I shift this point right here to the left 1, I'm here. If I shift this point at 9, negative 2 to the left 1, I'm at 8, negative 2. So this is negative log base 3 of x plus 1. So I have a vertical asymptote at x equals negative 1, and I'm going to go from negative 1 all the way to infinity. I want you guys to try this one. This is negative log base 4 of x minus 4 plus 3. So keep in mind what the reflection does. It flips it over the x. This will move it right 4. This will move it up 3. So you guys pause the video and see if you can graph that one. So as we come back and look at this one, we're going to look at how to put in log in the calculator. So I'm going to bring this one up. We'll do it on the calculator. Clear what's there. And I'm looking at the equation y equals negative log base 4. Negative log base 4 of x plus, let's see, x minus, I can't tell what that is, x minus 4 plus 3. So how do we get log to come up in our equation? If we go to math, all the way down to A, you see log base. Okay. Put that in there. We can type in any base and anything in parentheses that we want. It's log base 4. Move over. It's going to be x minus 4. I'll move over. We're going to have a plus 3. And I graph it. Okay. you want points, go to second table, and you'll notice that the points start at 5.3. We got one at 8.4. I'm going to try to use the whole numbers here. 11 and 4.4 is the next one. So if we go back and we plot these, plotted at 5.3. We got one at 8.4. And 11, 4.4, so it starts to get out here. So at x equals 4, there is a vertical asymptote. So this graph gets really, really close, but never touches that line. So we're going to have a range, or excuse me, a domain of 4 to infinity. All right, that concludes today's notes on logarithms and graphing. If you have any questions, remain on the Zoom, and we'll talk to you tomorrow.